Hello everyone, welcome to a new lecture in the series of control of mechanical systems. In this lecture, we will be discussing model predictive control of inverter pendulum. Here is the overview of this lecture. We will be starting with a brief introduction to model predictive control or MPC. Then we move on to MPC of inverter pendulum. Model predictive control or MPC uses model-based optimization for computing the control input. In MPC, a model of the system is used for predicting the future behavior of the system over a finite horizon known as the prediction horizon. The predicted behavior is characterized by a cost function, which will be a function of the predicted state or output sequence and the control input sequence. Then the control input sequence is computed for optimizing the cost function by using some optimization algorithm. The key features of MPC is that it results in a closed loop control scheme in which the current input will be a function of the current state or output. And the MPC can handle nonlinear higher order and multivariate systems. And the MPC can incorporate constraints on the states, outputs, or inputs easily. For more details on model predictive control, the lecture series on MPC can be referred, for which the link is given in the description. Next, we move on to the MPC of inverter pendulum, in which we will be considering the inverter pendulum system, which is discussed in the previous lecture. And we have derived the state space model of the inverter pendulum in the previous lecture, which is summarized here as in equation number 1. Here we have a nonlinear model with the 4 number of states denoted by x1, x2, x3, x4, and 2 outputs, which are y1 and y2. So here the states are x1 is angular position of the inverter pendulum, x2 is the angular velocity of the pendulum, x3 is the linear position of the cart, x4 is the linear velocity of the cart. In general, in the MPC, we normally use discrete time models for predicting the output or state. So therefore, we will be discretizing this model for obtaining the discrete time state space model. Here, this entire function we can represent as f of x and u, which is a continuous function of x of t and u of t, where here t stands for continuous time. Now using the Euler discretization, we can find the discrete time equivalent of this state equation as xk plus 1 equal to xk plus t into f of xk uk, where t stands for the sampling period, xk stands for x of k into t. This f function is same as this f, where we replace x of t with xk and u of t with uk. So this x2 will stands for x2k, x1 will be replaced by x1k, and u will be replaced by u1k, and so on. Similarly, we can have the output equation as yk is equal to c into xk, where c is this matrix, and these variables will be replaced with their discrete equivalent. In this lecture, we will be implementing a state-based MPC. So we will be only using the state equation part of the inverter pendulum, and using that we will implement an MPC scheme. Here we are considering the stabilization problem of the inverter pendulum. Therefore, the cost function for MPC can be used as in equation number 3, where Q and R are the weighting metrics for the state and control input, and Qn stands for the terminal weighting matrix. And here each time instant k, we compute the cost for the next n instance, where this cost is summed from k to k plus n minus 1, and we added the terminal cost to it. And this will result in the cost function for the MPC, which is optimized. Here our objective is to make the states value to converge to 0, which means the angular position, angular velocity of the pendulum should be 0, and the linear position and the linear velocity of the cart should be 0, which means the pendulum should be at the equilibrium position. For the simulation, we select the parameters of the pendulum as in this equation 4, and the weight matrix are chosen as Q as a 4x4 identity matrix, and Qn is selected as 5 times Q, which means like we are giving more weightage to the terminal cost, and R is chosen as 1. Here we have selected the initial position of the cart as 1, and our objective is to drive the cart from the position 1 to the position 0. While moving the cart, the angle of the pendulum will get affected, and therefore we update the control input to the pendulum in such a way that the angle should be come back to 0, and we need to maintain the angle as 0 and the angular velocity as well. This basically comes under the stabilization problem. Now with the MPC algorithm, figure 1 shows the plot of the cart angle and the angular velocity. Here we can see that the initial value was 0, but due to the movement, the angle gets affected, But with the control action, we were able to make the angle to 0 back. And the angular velocity will also be getting affected, eventually able to control it back to 0. This plot shows the cart position and velocity. So here we have the initial position was 1. Then it is gradually decreasing and converging to 0 after a slight overshoot. And here we can see the linear velocity of the cart, which is also starting from 0. It changes from 0 due to the cart movement, and eventually it becomes 0 again. Which means that the MPC, we were able to stabilize the inverter pendulum system. And this figure shows the control input for the inverter pendulum, which is basically the applied force on the cart. And here we can see that the force is between -4 and 0.2. The MATLAB codes for this MPC implementation can be downloaded from the link given in the description. That leads to the end of this lecture. Thanks for watching.